Hello and welcome. In a previous video, we took a look at n-dimensional space, which is kind of just the idea of taking what we're familiar with a number line and with coordinates in two-dimensional space and extending that into coordinates in 3 dimensions and beyond. Now, we did take a look a little bit of geometry in there, especially being able to find the distance between 2 points. Now, what we're going to be doing in this video is taking a look at vectors, which is kind of this new construction. It's something that we can take a look at that has a direction in as many dimensions as we want. It's just the idea of a quantity that also has a direction. So let's see what the difference is between a vector and a scalar first of all. Now, vector is what we're talking about here with magnitude and direction, and some examples of that would be something like displacement. And displacement is nothing more than the difference between 2 positions. Velocity, acceleration, force, these are all quantities that have some kind of units to them typically, and also has a direction in which it's pointed. Whereas a scalar is just a directionless quantity. Things like mass, charge, and area, well, they don't have a direction. I mean, charge certainly could be positive or negative, but it's not in a particular direction, really. Now, distance here can be a little bit of a tricky one. Displacement, again, is just the difference between 2 positions. So you could travel a great distance all around the province and perhaps come back to where you started, but that would mean your displacement is 0. Speed and velocity are kind of a similar sort of relationship where speed also doesn't have a direction, but has the same units as velocity. And acceleration is a vector, but we can talk about simply just the magnitude of acceleration as being a scalar. Well, with that out of the way, let's take a look at vectors in 1 dimension first. Now, it's a bit of a silly example. In 1 dimension, we simply just have the real number line. So when we're talking about, let's say, a displacement of 5 units, there's only 2 directions we can look at. We could have a displacement of 5 units to the right, which would be plus 5, or we could have a displacement of 5 units to the left, which would be negative 5. So honestly, that plus and minus really already give us a direction. Note that we can have that 5 units of displacement to the right and still not know where our initial and terminal positions are. Okay, well, let's take a look at a vector of 5 units in 2 dimensions. This vector, this arrow, which has got a magnitude of 5, could be in any direction. For instance, let's say it's pointing slightly up and to the right, which isn't really all that technical of a direction. Better off, we might be able to think about a direction as being some kind of angle, maybe measured from the positive x-axis. That's not necessarily the best way of actually describing a vector. Oftentimes, it's more useful to think about what component of that vector is in the x and y direction. For instance, maybe that vector of 5 is actually kind of like a displacement of 4 units right and 3 units up. Those 2 displacements together form this 3, 4, 5 triangle. You can see 3 squared plus 4 squared equals 5 squared by the Pythagorean theorem. Well, in that case, it's probably better to actually list the components of this vector so you know exactly which way it's pointing. Much like with a point, we're going to use an ordered pair here. Our x component is 4 and our y component is 3, so this would be the vector 4, 3. But you'll notice that we're using triangular brackets for vectors and round brackets for points. Now you can do the same thing with 1-dimensional vectors, although it's not really necessary. We have, for instance, 5 in triangular brackets, meaning 5 units to the right. But it's pretty obvious because 5 units to the left would simply just be negative 5, and the triangular brackets don't really do anything for us. So we really don't start thinking of vectors until we get to 2-dimensional space. Okay, well, let's just extend this to 3-dimensional space then. Here's a vector in 3-dimensional space that also has a magnitude of 5. Now, in first octave view, it's almost impossible to know which way this is pointing. Better off, let me give you the components of that. Let's suppose that that 5 magnitude actually has a magnitude of 3 root 2 in the x direction, 1 in the y direction, and root 6 in the positive z direction. Well, in that case, then we could just label that vector in component notation 3 root 2, comma 1, comma root 6. And that tells us exactly how many steps to take in each of those 3 different directions to get the overall vector of 5. So in general, in n-dimensional space, a vector would have n components. A1, A2, A3, and so forth, all the way up to AN. And we might just call this the vector A. And with a special notation here, we have A with a little arrow over the top. That arrow indicates that this is a vector. And we can then maybe use just the shorthand notation A with a vector arrow in various different calculations in the future. Now, it's really important for me to mention here that there is a little discrepancy in notation depending on where you see it. Now, when mathematics is properly typeset, that means typed up for something like a textbook or a research paper, for instance, not everybody will necessarily choose to use that little vector arrow over the top, although it is quite common. Sometimes you can just get away with having vectors being bold typeface, or just bold font, and you'll be able to tell those right away compared to the scalars and other operations that won't be bold. And we'll be doing operations on vectors later on in this video. It is really important to know what kind of objects you're dealing with when you're simply just writing down their names. So make sure when you have a vector, you write this little arrow over the top, or if you're just typing at math, maybe make it bold. I prefer using the vector because it's very obvious that way. Now, remember, as I mentioned earlier, that a vector has magnitude and direction, but it doesn't actually specify the initial and terminal point. However, if we're given 2 points, then we should be able to find a vector from one point to the next. Let's try a little example. Let's suppose that we're given a point P, 5, -2, -1, and a point Q, -2, 1, 1. Well, if P is our initial point and Q is our terminal point, then the vector from P to Q can simply just be written in this nice shorthand notation, PQ, with a vector arrow over the top. That already tells us the order from one point to the next. In order to calculate that vector, we need to take the terminal point, Q, have its components, and subtract the components of our initial point, P. So that would give us -2 minus 5 for our x component, for instance. For our y component, we'll have 1 minus -2, and for a z component, 1 minus -1. Simply just taking the differences in the x, y, and z components correspondingly. This gives us the vector -7, 1, 2. If we wanted our terminal point to be P and our initial point to be Q, it would just simply change the order in which we're subtracting, in which case we would have QP be the vector 7, -1, -2. And you notice that each component is simply negated. Now, before we take a look at computing the magnitude of a vector given its components, it's really helpful to know that whenever we decide to have a vector's initial point be the origin, we say that it is in standard position. Given a vector A with the component A1, A2, A3 up to AN, if that initial point here is 0, and that is simply just the component 0, 0, 0 all the way up to 0, then that terminal point is the same n tuple as the vector. It's just that the terminal point is a point, so it has round brackets, and the n tuple of the vector, being a vector, has triangular brackets. Now, that will give us a great way to find the magnitude of any vector. We just calculate basically the distance between the origin and that terminal point. Now, we have a special term for this. We say that the magnitude of a vector is called its norm. The notation for this is when we had a vector, let's say A, then we put A in double vertical bars, kind of like having a doubled up absolute value. And it is simply just the sum from I equals 1 to n of each component squared. And then we take that sum and we square root it. This is exactly the same as finding the distance between the origin and the terminal point of the vector in standard position. In the case where we only have one dimension, of course, it's not really much of a vector A is simply just a single component, A. It can only be positive or negative. Well, then the magnitude of that vector A would be the one component, which is A, squared, and then square rooted. That's actually the same thing as the absolute value. So it kind of makes sense that this norm and the absolute value have very similar looking symbols. In fact, another common sort of discrepancy of notation that you'll see is that sometimes the norm of a vector is simply written as absolute value. It kind of makes sense as long as you can tell whether or not that object is a scalar or a vector, then you already know what absolute value should do. If you see that vector symbol, or if it's got that bold font and it's inside an absolute value, you can't just simply take each component and make it positive. That's what we do with scalars or simply one-dimensional vectors. If you see the absolute value around a vector, then we actually have to apply this norm formula, take each component squared, add them together, and then square root. So for instance, in R2, this vector A would have two components, A1 and A2. And whether or not the norm is written with double vertical bars or simply with a single vertical bar on each side, we have to do the computation A1 squared plus A2 squared and then square root that whole thing. And then this can simply be extended to as many dimensions as we like. You'll see this in R3 very often, with the components A1, A2, A3, each being squared, summed together, and then square rooted. Now, if we go back to this previous example here, you can see that, of course, in R2, I have this example where I have 3 squared plus 4 squared equals 5 squared. That gives us a length of 5. And this other example in R3, 3 root 2 squared plus 1 squared plus root 6 squared equals 25. And by square rooting that, we get 5. Now, it is quite possible that the norm of a vector might just equal 1. That would mean that basically the length of that vector arrow is 1 unit or has a unit length. Well, if that's the case, we call it a unit vector. And I like to use a special notation for unit vectors. A unit vector is just like any other vector. We typically put an arrow over the top, but I choose to use a little hat. So A with a little hat over that means it's a vector with a unit length. Now, of course, as I mentioned a couple times already, notation does differ from one source to another. So while this hat notation is very convenient for being able to tell you that A, it's a vector, and B, it has a length of 1, a lot of times we'll just get away with saying it's a vector and we'll just have an arrow over the top. Both are equally accurate. It's just that the arrow notation doesn't implicitly tell you that it has a length of 1. And same thing with just making this a bold typeface if it's printed. Bold would typically mean it's a vector, but again, it doesn't tell you quite as much information. It doesn't tell you that it has a length of 1. You'd have to either intuitively know that or be able to deduce that from something else. So typically, I would recommend using this hat notation when you specifically mean for it to be a unit vector. Now that we've got the basics of vectors with direction and magnitude and components, what we can do next is kind of the same thing you do whenever you come up with new forms of numbers in general. How do you put two of them together? For instance, what do we do if we have two vectors and we want to do something like add them? That'll be our first operation on vectors, simply just vector addition. Let's start off with two vectors. Let's suppose vector A here is in standard position at the origin. I don't necessarily know what the components of it are, but it definitely goes from the point 0, 0 up to this other point here at the top right. Well, let's take a look at a second vector. We'll call it B, and here it is also in standard position. What if I wanted to add the two vectors together? How do we do that? Well, it might help to intuitively think about these two vectors as displacement. So for instance, let's start off with A. And I'm traveling from the initial point 0, 0 in the direction of A with that particular magnitude, and I'll end up at this point here at the top right. From there, I'm going to add an extra displacement, B. That's going to take me from my new initial point at the tip of the arrow from A, and it's going to make me travel in the direction of B. So it might help if I actually move that vector up to the terminal point of the first vector. And you can see now that I've got my initial point of B at the terminal point of A, and my terminal point of B is at this new point. Overall, my path has taken A and B. And remember, with displacement, the overall displacement is just simply the difference between the initial and terminal points. So it doesn't really matter what my path was. My overall displacement will simply be from one point, 0, 0, to this new terminal point at the end. So this vector, in purple, is the vector A plus B. I'm summing up two displacements, and to do that, I only need to look at the terminal point of B when its initial point is placed at the terminal point of A. We call this tip-to-tail graphical addition, and it kind of makes sense in other applications other than just displacement. For instance, another very common form of vector is force. So for instance, the other day I was just riding my bicycle up in southeast Kelowna, and it was a bit of a windy day. Well, the first thing you'll notice here is that this blue vector, that one, the force on the bike, that's me pedaling. That is me trying to keep the bike on the road, and I'm pushing pretty hard to try to keep it going in a forward direction here. The wind was a headwind, and you can see that it's pushing me backwards. It was also trying to push me off the road slightly here, and that's why my forward force is also going off the road in the opposite direction to compensate. Well, overall, imagine that my bike is still going forward. Well, it makes sense here when we take a look at that tip-to-tail addition. When we take the force on my bike and add the force from the wind, you can see that I'm still traveling forward here. The overall net force is basically just exactly along this bike lane. Now, while graphical addition can be really useful for visualizing how we add two vectors together, particularly in 2 dimensions, it doesn't really help us as much as actually having a computational form. Luckily, the computational form is quite easy. We simply just add corresponding components of A and B together. So we'll have A1 plus B1, and A2 plus B2, and so on and so forth until we get to the nth component of each vector, AN plus BN. Thinking about displacement again, it's really just taking a look at the individual displacements in each direction. Or force is taking a look at the sum of the forces in each direction. Now you can probably imagine that subtraction is very similar to addition, and it is, but it may be useful first to talk about a form of multiplication first. There are different multiplication operations on vectors, but the one we want to take a look at first is called scalar multiplication. Now, scalar multiplication is kind of the easiest multiplication operation that we can take a look at on vectors. For instance, let's just imagine that we have A plus A plus A. Now, graphically, that's just taking a vector, A, let's say that's this blue arrow, and then adding, using tip-to-tail addition, A again, and then adding A one more time. Now, as you can see here, we haven't changed direction at all. We've simply just taken the magnitude of that vector and multiplied it by 3. In fact, we would say A plus A plus A is simply just equal to 3A. We've taken A and we've made it 3 times its length, but it is still the same direction. With scalar multiplication, we can create a brand new vector that is parallel to the original, but just has a larger or smaller magnitude. Now, we can also have any scalar. You can imagine that 5A is just going to be 5 times the length, and 1/2 A is going to be 1/2 the length. So we can take any scalar and multiply it by A. What about a negative number? What happens if we have negative 1A? Well, let's pretend that we have our vector A in standard position. What does it mean to take a vector and multiply it by negative 1? Well, as you can imagine, in 1 dimension, that simply is just like 5 and negative 5. They go in opposite directions. It's the same thing in n dimensions. Negative 1A is exactly the same vector, but in the opposite direction. And you'll see that that is actually still parallel with A. Negative 1A is simply just in the opposite direction. And we'll typically just write that as negative A. We won't actually write that 1. So A and negative A have the same magnitude, but exactly opposite direction. In general, scalar multiplication is a pretty easy thing to do. C could be any scalar, and C times A is simply just taking C and multiplying each component. That would be C times A1, comma, C times A2, and so on and so forth. And remember that when we take a vector and multiply it by a scalar, we end up with a parallel vector, either in the same direction or in the opposite direction. But the converse is also true. 2 vectors, A and B, are parallel if there exists some scalar such that B is a scalar multiple of A. That's a quick way of being able to check if 2 vectors are pointing in the same direction or in exactly the opposite direction, depending on whether C is positive or negative. Now that we've got scalar multiplication as well as addition, this kind of already produces subtraction as well. If we wanted to look at a minus b, well, that's just vector addition of a and negative b. So we just take all of the components of b and negate them and add them on to all the components of a, which is no different than simply subtracting corresponding components of a and b. So as you can see, addition and subtraction of vectors work in exactly the same way by combining these two operations together. Let's take a look at a quick example of vector addition and scalar multiplication of two vectors in two-dimensional space so that it's a little easier to visualize. Okay, in this example, we've got the vector a, which is 4, negative 2, and b, which is negative 2, 3. Let's suppose we want to compute the vector given by 1/2 of a plus 2b. This will combine both scalar multiplication as well as vector addition. It may help to write down the same equation, but using our components first. 1/2 of 4, negative 2 plus 2 times negative 2, 3. And let's start off with scalar multiplication first. That means that we're going to take each component of a and multiply that by 1/2. And we'll take each component of b and multiply that by 2. From there, now we can go ahead and use vector addition and add corresponding components of those two vectors. That would be 1/2 of 4 plus 2 times negative 2, comma, 1/2 of negative 2 plus 2 times 3. Overall, that gives us the resultant vector negative 2, 5. Now graphically, let's see if we can reproduce that. First thing we're going to have to do is we're going to have to take this vector a and we're going to have to reduce its magnitude. We're going to take this vector a, we're going to make it half the length. Okay, now we have 1/2 of a. Now with b, we're going to have to make that vector double its length. All right, that is 2 times b now. Now that we've done the scalar multiplication, now we can use our tip to tail addition. Now it actually will work out that 1/2 a plus 2b is equal to 2b plus 1/2 a by the commutative properties of addition. But since we have it specifically written as 1/2 a plus 2b, let's take this 2b and use tip to tail addition by placing its initial point at the terminal point of 1/2 a. Well then, let me just move this text here a little bit and we can take a look at the resultant vector. That seems to be 2 units to the left and 5 units up. So that confirms what we just computed by using component-wise addition and scalar multiplication. Going back to what we were just talking about a moment ago about norms, we have a very convenient theorem for calculating the norm of a scalar multiple of a vector a. Let's suppose that a is a vector in Rn and c is a scalar. That means it's just a real number. Then the norm of c times a, that's just taking the length of a and scaling it by c, only with the fact that we have to also make sure that its length is still positive. So even if c is a negative number, we need this to be a positive value. So another way to compute that is by taking the absolute value of that scalar multiple c and simply multiplying that by the length of the original vector a. That gives us the length of CA overall. If the length of a vector happens to be equal to 0, well, then we call that the 0 vector. And there is only one 0 vector. The 0 vector is kind of unique in the fact that it doesn't have a direction. We would say that the 0 vector is simply the vector where every component is equal to 0. And it's denoted as 0 with a vector symbol over the top. Or of course, it could just be a very bold 0 in the case where you use boldface type for vectors. Now this theorem on its own might seem a little bit obvious because essentially a scalar multiple of a vector is doing nothing to it other than changing its length or possibly switching it to the opposite direction. But it can be really useful in this particular example. Let's suppose that we're given a vector v, which has components 2, negative 1, 3, and we wish to give a vector, let's say u, in that same direction but having a unit length. So it might actually make more sense here, instead of u with a vector symbol, that we could just have u with a little hat over the top. Unit vectors are going to be particularly useful later on in this course because it has a very nice length of just 1, and it really just only tells us a direction. Now remember, if we want u hat to be in the direction of v, then it must be a scalar multiple of v, and it has to have a positive scalar c. That way it's not going in the opposite direction. The other requirement is that we need to have the norm of u hat equal to 1. Well, using that equation that u is equal to c times v, then the norm of u hat must equal the norm of cv. And by this theorem, that is equal to the absolute value of c times the norm of v. Well, since c is positive, then the absolute value is simply equal to c. We can calculate the norm of the vector 2, -1, 3 using the formula, and that gives us the square root of 14. So the norm of u hat is equal to c times root 14. But we want that to equal 1. If c times root 14 is equal to 1, then we can solve for c, and that gives c is equal to 1 over root 14. And once we know that, we can then write out our vector u hat. U hat, remember, is equal to c times v, and that's equal to 1 over root 14 times 2, -1, 3. And this is the vector that we meant to find. This is going to be a vector of unit length in the vector of v. Although if you wish, you could use scalar multiplication and rewrite that as 2 over root 14, -1 over root 14, and 3 over root 14, although either one of these notations is correct. Now, last but not least, now that we've got the idea of unit vectors, as well as we have this idea of component-wise addition, what we can actually do is we come up with some sort of standard unit vectors and show that you can create any vector you like in n-dimensional space by simply just adding up each of these special unit vectors. We call them elementary unit vectors. It's probably best to visualize these elementary unit vectors in 3-dimensional space first. As you can probably imagine, we can write any vector in R3 as the sum of a vector with a unit length in the positive x direction, a vector of unit length in the positive y direction, and a vector of unit length in the positive z direction. Since any vector has an x, a y, and a z component in R3, we can just simply have scalar multiples of the blue, red, and green vectors added together to create whatever vector we like. We give them special names, and since they're all unit vectors, I'll use hats. The unit vector in the positive x direction is I hat. The unit vector in the positive y direction is j hat. The unit vector in the positive direction, you probably guessed it, is k hat. If we were to have I hat plus j hat plus k hat, then we would have the vector 1, 1, 1. In 3-dimensional space, we need 3 of these elementary unit vectors. However, if we only are dealing with R2, then we only need 2 elementary vectors. We can imagine what this would look like in as many dimensions as we want. The vector I hat always points in the direction of the positive x-axis. So if we were just to have single dimension R, then I hat is really just the number 1. Not -1, but +1, pointing in the positive x direction. However, the moment we jump to R2, then that vector in component notation would be the vector 1, 0. And at that point in time, we're going to need a second elementary unit vector, and that would be j hat. And that's going to have the components 0, 1. I and j will then be able to construct any vector you like in R2. We say it forms a basis for R2. Any vector, a1, a2, can be written as some sort of scalar multiple of I plus a scalar multiple of j. And then, of course, as you see here in this picture, the moment that we go to 3 dimensions, we need to have a third vector. At this point in time, in component notation, I would be the vector 1, 0, 0, and j would be the vector 0, 1, 0, and along comes k with the component notation 0, 0, 1. Once we get maybe past 3 dimensions, it might not make quite as much sense to use I, j, k, and l anymore, especially since l kind of looks like a 1, and many other things could get confused with that. It's better off, maybe with many dimensions, to simply just use maybe a new notation here. In Rn, we might say that these elementary unit vectors are just e1 hat, e2 hat, and e3 hat. That would be our I, a j, and a k again, just with a little bit more bland notation instead. E4, E5, and E6, and so on, all the way up to the nth dimension. Well, these are all going to be similar looking vectors. They're going to be mostly zeros, but EI would have a 1 in the ith position in that n tuple. So it's just going to be all zeros except for a single 1, and that would be in the positive direction of the ith axis if we could draw all of these n axes. The nice thing with these elementary unit vectors is that we could actually get rid of this component notation whenever it's more convenient, and instead write out a vector using scalar multiplication and vector addition as just a linear combination of the elementary unit vectors. For instance, in R2, if we have the vector A equal A1, A2 in component notation, we could write that as A1, a scalar, times I hat, a vector, plus A2, another scalar, times j hat, a vector. And you can see that is equal to A1 times the vector 1, 0, plus A2 times the vector 0, 1. And of course, that scalar multiplication just gives us A1, comma 0, plus 0, comma A2. Adding component-wise, sure enough, that is equivalent to A1, comma A2. The elementary unit vector notation actually has a lot of advantages when we start taking a look at calculus applications later. Plus, we're already pretty good with addition of common terms. And so if you have multiple vectors together and we add up all of the I hats, well, that's exactly the same way as vector addition works, by adding all of the corresponding x components. So it does have quite a few advantages there. In R3, then our vector A1, A2, A3 can simply be rewritten as A1 times I hat plus A2 times j hat plus A3 times k hat. And as you can imagine, it's a little bit more cumbersome to say, so you might just see A1i plus A2j plus A3k and just omit those hats. It's kind of already implied. Finally, when you start getting to our nth dimension, then we would just have to go ahead and write this all out in terms of the EI hats. A1, E1 plus A2, E2 all the way up to AN, EN. And we'll see this notation again quite a lot in the future. But for now, I think that's probably a good place to stop with the idea of just the basics of vectors. Now, there are other operations of multiplication that we're going to be taking a look at in separate videos. All we've done so far is taking a look at taking a vector multiplied by a scalar. There are two different kinds of objects, really. We're taking a scalar, which is just a number, directionless, and multiplying a vector. So the direction comes from the vector, and all we can do is potentially have an opposite direction if that scalar multiple is negative. The other multiplications we'll be taking a look at are multiplications between two vectors, and of course those aren't quite as intuitive, so we'll cover each of those in a future video. Thanks for watching, and I'll see you in the next video.